The purpose of this video is to demonstrate how we can use the LINEST function in Microsoft Excel in order to calculate regression statistics associated with a calibration curve. In the first video of this series, we completed tasks 1 and 2. In this video, we will complete tasks 3 and 4, which involves using the LINEST function to determine regression statistics associated with the calibration curve we built in the first video, and we will learn how to calculate 95% confidence intervals for the slope and the y-intercept of a calibration curve. So let's scroll down a bit, and in order to apply the LINEST function, we need to select a 3x2 matrix of cells, at which point we will type the formula equals LINEST for LINEST, open parentheses, and then Microsoft is giving us hints in terms of which arguments it wants in which order. So the first argument are the known y values. So all we have to do is go up to the y values that correspond to our calibration curve, and we plotted corrected detector responses on the y-axis. And so we'll come up to the blank corrected detector responses that were included in our calibration curve. So we're not going to include the blank or the highest calibration standard that was excluded from our linear regression. To get to the next argument, we'll enter a comma, and then the next argument are the known x values, which are the corresponding concentrations of our analyte acetaminophen. Another comma takes us to the third argument, which is the constants. Microsoft Excel is telling us that if we enter false for this argument, since this is a true-false argument, b, the y-intercept of our calibration curve, will be set equal to 0. In other words, it will be forced to go through the origin if we enter false for this argument. On the other hand, if we enter true, then the y-intercept b is calculated normally, which is what we want it to do. And so we will virtually always select true for this argument. You can either type true, click true, or you can enter the number 1, which in a true-false argument corresponds to true, and the number 0 corresponds to false. We'll enter another comma, and then we have another true-false argument. True meaning that we return the additional regression statistics, and by return, Microsoft Excel means display. False means do not display the additional regression statistics. And sure, we'll select true so that we can see all of the regression statistics that Microsoft Excel can give us. That's all 4 arguments, and so we'll do close parentheses. Now here's where the LINEST function is special. At this point, I cannot just click enter. I must push and hold Control, push and hold Shift, and then select enter in order to get all of the 6 cells to populate with data. Okay, so I'm just going to add a border to these LINEST output, and let's just label these as LINEST output. Let's also go ahead and label what each of these 6 values denote. So in the upper right hand corner is the slope, or the m value. This next value is the standard uncertainty in the slope, which is called u sub m. The bottom left value is the r squared value. The upper right value is the y-intercept of the linear regression, or b, in y equals mx plus b. The next value is the standard uncertainty in b, the y-intercept. Dan Harris's textbook refers to this as u sub b, and the lower right corner is the standard uncertainty in y, or u sub y. That is the LINEST output. Next, I want to illustrate how we can calculate the 95% confidence intervals associated with the slope and the y-intercept. In order to do so, let's identify some of the additional statistics associated with this linear regression. For our linear regression, I would like to determine n, the number of data points included in the linear regression. In order to do that, I'm going to enter equal sign, count, and then highlight the cells, and we can just pick the y-axis values, for example, all of the cells that were included in the linear regression. And so Microsoft Excel is just going to count how many entries are present there. And we get a number of 7, of course. So if we just counted the data points that were included in our linear regression, we would end up with 7 as well. The degrees of freedom formula for a linear regression is equal to n minus 2. That's because a linear regression represents two-dimensional data, or y versus x data, where the degrees of freedom formula is n minus 2. That allows us to calculate the degrees of freedom as equal sign, selecting n cell, minus 2, or 5 degrees of freedom. Now we can use Microsoft Excel to look up the student's t-value at the 95% confidence interval. We can do that by entering the formula equal sign TINV for t-interval, open parentheses. The first argument is the probability. By probability, Microsoft Excel means 1 minus the confidence level. In this case, we're using the 95% confidence level, so 1 minus 95%, or 1 minus 0.95, is 0.05. Degrees of freedom, we will just select the cell for degrees of freedom, close parentheses, enter. And so Microsoft Excel looked up the t value at the 95% confidence interval for 5 degrees of freedom. This value is also available in tables in your textbook, but it's convenient that Microsoft Excel can look that up for us. One thing I want you to appreciate about how we're constructing these arguments and these formulas in Microsoft Excel is that whenever possible, we are referring back to a previous cell. I could have, for example, in the student's t-interval function, instead of referring back to the degrees of freedom formula, I could have just typed in the number 5. I didn't have to refer back to a cell. But the advantage to referring back to a cell is that if I made changes to this spreadsheet, let's say I ended up not having as many calibration standards. If I am referring back to previous cells, you'll see that these cells are automatically updated to reflect those changes in my input data. That's a really useful feature of a spreadsheet, and it's something you should get in the habit of doing, of whenever possible, refer back to a cell rather than typing in a number. And so I'm going to push Control Z a few times to undo those changes to my input data. At this point, I have everything I need in order to calculate the 95% confidence intervals for the slope and the y-intercept. I've labeled 2 additional cells for the 95% confidence interval of the slope and the y-intercept. The formula for a 95% confidence interval associated with two-dimensional data, and since we're using a linear regression, and so these are two-dimensional data, the 95% confidence interval for the slope we can calculate as the t-value, so I'm going to enter equals and then refer back to our t-value, multiplied by the standard uncertainty in the slope, U sub m. Similarly, the 95% confidence interval for the y-intercept is equal to the t-value multiplied by the standard uncertainty in the y-intercept, which is U sub b. These 95% confidence intervals are examples of absolute uncertainties, and so they have the same units as the slope or the y-intercept. And so just to emphasize that point, let's label those units for slope and y-intercept. Unlike 95% confidence interval equations for one-dimensional data, which is s times t divided by the square root of n, for two-dimensional data, we're not dividing by the square root of n for these 95% confidence interval formulas. It's just the standard uncertainty multiplied by the t-value. One last thing that I'll point out in this video is that the LINEST output should agree with the output that the linear regression on your graph indicate. The number of significant digits shown might vary from this linear regression label compared to the LINEST output, but that's something that you could change. And so if I wanted to be absolutely sure, for example, that these values were the same, I noticed that, for example, the y-intercept is being shown to 4 significant digits here. I can right-click and select Format Trendline Label, and then under the number category, I can select number and then specify how many decimal places I want to show. So if I want to show 4, then it will show 4 decimal places in the y-intercept, in fact in all of the values that are shown there. And so I can change this to whatever value that I want. Importantly, I need to show enough decimal places here in this label so that the r² value doesn't get rounded to 1. So for example, if I were to change this to say 2 decimal places, you see how Microsoft Excel is rounding this r² value to 1? That robs us of some really important information, because analytical chemists want to know how many 9s exist after the decimal point in your r² value. But if you're rounding this value to 1, we lose track of how many 9s are present. And so I encourage you to set the number of decimal places so that the r² value does not get rounded to 1. So in this case, that would mean showing at least 4 decimal places to get it not to round to 1. This concludes this video.